Welcome to the debate. So imagine for a second that you are incredibly thirsty, like parched.
Just dying for a drink.
Right. You see a glass of water on a table, and your brain just lights up like a pinball machine. But if you had just chugged a gallon of water and you aren't thirsty at all, that exact same glass of water triggers almost zero brain activity.
Which is wild to think about.
It is. So why? How does your brain actually know when to care?
Honestly, I think it's one of the most fascinating questions in modern neuroscience. Just, how our internal homeostatic states completely alter our perception of the outside world.
Exactly. And at the absolute center of that question is a massive controversy over two chemicals that I'm sure everyone has heard of, dopamine and serotonin.
Oh yeah, the heavy hitters.
The heavy hitters. Historically, we've thought of them as this classic battle of opposites. Dopamine wants to go, it chases reward. Serotonin, on the other hand, says stop. It urges patience.
Right, the whole gas and brake pedal analogy.
Yeah, and I'll be arguing that this analogy actually holds up. I look at the data, especially the recent studies on how drugs like MDMA affect the brain's reward centers, and I see clear structural opponency. Dopamine is the accelerator and serotonin is the active opposing restraint that basically keeps us from careening off a cliff.
See, I think that stop sign theory is just way too reductive. I'll be taking the stance that they are actually highly synergistic. Serotonin isn't just mindlessly slamming the brakes on dopamine, it's actively setting the stage so dopamine can do its job safely. I see it as a state-gating mechanism.
Okay, well, let's just start with what we physically observe when an animal is learning to wait for a reward.
Sure.
If you look at the data, as a predicted reward gets closer and closer, serotonin levels steadily ramp up.
They do, yeah.
And to me, that is the literal mechanism of holding impulsive dopaminergic action in check. It's an active restraint. It holds you back until the conditions are absolutely perfect.
But serotonin is doing so much more than just inducing a state of waiting, though. It is actively managing windows of receptivity.
What do you mean by windows?
Well, think back to that thirsty mouse paradigm you opened with. When the mouse is totally sated, the sensory cue for water does nothing.
Right.
But when that homeostatic drive, the thirst, is active, that exact same visual cue triggers a massive wave of activity across, I think it's 34 distinct brain regions.
Yeah, it's a huge systemic response.
Exactly. The brain is effectively opening a window. Serotonin and dopamine rely on this gated receptivity to function together. You aren't braking. You are globally sensitizing the system to the reward.
Hold on. I see why you think that, but let me give you a different perspective. If serotonin is essentially just gently opening a window of receptivity based on homeostatic need, how do you explain the PBWM models?
The prefrontal cortex basal ganglia working memory models?
Yeah, because in those computational frameworks, dopamine bursts and dips alone dictate what we learn. A positive dopamine spike reinforces the go pathway, and a dip reinforces the no-go pathway.
Right, the prediction error.
Exactly. Doesn't the dopamine prediction error act as the ultimate gatekeeper of what we learn, regardless of what serotonin is doing in the background? Dopamine is the bouncer at the club.
I mean, dopamine prediction errors are brilliant. I'll definitely give you that.
Thank you.
But, and this is a big but, they are brilliant for simple, trial and error associative learning. In a complex, completely unpredictable world, the brain has to know when it's actually safe to use those prediction errors.
Safe in what way?
In the sense of not panicking. Serotonin provides the contextual safety net required for those dopaminergic updates to actually be encoded, without triggering aversive or defensive responses.
Okay, but that safety net you're describing completely falls apart when we look at addiction and neuropharmacology.
How so?
Let's look at the nucleus accumbens, which is a major reward center in the brain.
Right, the NAC.
If we introduce a chemical blocker into a lab animal that temporarily blinds its brain to serotonin, specifically blocking the 5-HT2C receptors, the dopamine reward response to a drug like MDMA just goes entirely off the charts.
Well, we measure that through condition-place preference, right?
Yes, their behavioral preference for where they receive the drug skyrockets. So by physically removing serotonin from the equation, the dopamine reward becomes massive and unchecked.
I'm not denying the spike in reward.
But that isn't orchestration, right? That is a cage breaking open. It proves serotonin is actively suppressing dopamine-driven reward to prevent compulsive behavior.
Okay, the suppression is there. I acknowledge that constraint. But you're only looking at half the picture.
Which half am I missing?
You have to look at what's happening simultaneously with the other serotonin receptors. While it's capping that dopamine high via 5-HT2C, serotonin is also attaching to 5-HT1B receptors.
Okay.
And think of those as chemical locks that tell the brain's excitatory neurons to just quiet down. In neuroscience, this is called long-term depression.
Right, LTD, the weakening of the synapse.
Exactly. It essentially turns the volume down on background social anxiety and fear.
So you're saying it's actively blunting the fear response?
Yes, and this is a profound example of cooperative learning. Serotonin dampens the fear so that the subsequent dopamine jackpot reward can update complex internal models without triggering panic.
Huh.
Serotonin isn't a brake pedal, it's a clutch. It temporarily disengages the engine so you can, shift gears safely without destroying the transmission. It's making the brain's architecture receptive to the dopamine update.
Okay, I genuinely like the clutch metaphor, but I'm not fully convinced. Because with that analogy, you are fundamentally uncoupling the physical action from the reward.
Well,
Let me finish this thought. Dopamine drives the physical pursuit of rewards. And because it has that immense driving force, serotonin must act as the opposing force to stop us from just acting out every impulse. If they were purely synergistic, just happily shifting gears together, the system would run away with itself into compulsive action.
Wait, let's pause here for a second because this is a huge paradigm shift in the recent literature. If we look at the absolute latest findings, the rapid release of dopamine is actually completely dispensable for initiating movement.
Dispensable? Meaning an animal without rapid dopamine signaling can still physically initiate an action?
Yes, that's exactly it. Subjects can still physically move and initiate action just fine without it. Where they fail is in their reward responses and motivation.
Wow.
Yeah, this decoupling completely proves that dopamine and serotonin are not simply a motor, gas, and brake system. They are a sophisticated synergistic evaluator of emotional and motivational value. Dopamine isn't just mindlessly driving the car, it's evaluating the destination.
Okay, that is a crucial distinction. I will acknowledge that uncoupling action from rapid dopamine completely shifts our understanding of the motor system.
Right.
But biologically, the question still remains. How does a value assignment system balance these massive dopaminergic learning waves, these huge reinforcement signals, without a structural serotonergic opponency, keeping it from descending into compulsive behavior?
I don't think it descends into compulsion if...
But even if dopamine is evaluating value, rather than just driving a physical reflex, that value assignment still requires a rigid opposing constraint to prevent addiction, doesn't it?
It doesn't require a rigid constraint if it relies on state-dependent modulation. The system balances itself because the dopaminergic learning wave can only firmly take hold when the serotonergic system has primed the environment for it.
So it has to be allowed in.
Exactly. They work in tandem to ensure that high-value rewards update our internal models only when the organism is in a safe receptive state.
Well, we have covered a tremendous amount of neurobiological ground today.
We really have.
To summarize my position, though, I think the evidence, particularly how dopamine reward just explodes when we block serotonin in the nucleus accumbens, confirms the necessity of the opponent constraint. The brain requires that structural antagonism to regulate reward and prevent compulsive loops.
And to summarize my stance, I think when we look at how serotonin quiets excitatory anxiety and creates homeostatic receptivity, we see that these neuromodulators are deeply cooperative. They gate our neural states, sculpting the environment so that learning and social connection can occur safely.
I think where we absolutely converge, though, is on the sheer precision of this system.
Oh, 100%.
The interplay between these neuromodulators operates on a millisecond by millisecond basis, and it is utterly essential for updating our internal map of the world without fracturing it.
Completely agree. And, understanding this delicate balance isn't just some abstract academic exercise. It is critical for developing novel psychiatric therapeutics.
Right, like entactogens derived from things like MDMA?
Exactly. Drugs that can maximize pro-social therapeutic benefits while maintaining a very low abuse liability.
Parsing this neurochemical complexity truly illuminates the biological foundations of learning, of patience, and really how we connect with others. It turns out looking under the hood of the human brain, we aren't just looking at a simple mechanism to go or stop.
No, definitely not. We're looking at an incredibly sophisticated navigation system, one that asks us not just how fast we are going, but whether we are truly ready to take in the road ahead.
A perfect place to leave it. Thank you for listening to the debate, and we leave you to weigh the neurochemical evidence for yourselves.